Space is almost completely empty. There is no air between Earth and the Sun. No atmosphere connects us. No invisible tunnel carries heat across space. And yet every morning, the sun rises and warms your face, the ground, the oceans, and eventually, the whole planet. So how does heat cross 93 million miles of empty space? If you have been told that heat moves through warm air, this looks like a problem. There is no warm air between us and the sun. The answer is that heat travels in more than one way, and one of those ways needs nothing in between. Hold your hand near a hot stove. Do not touch it. You can still feel heat. Some of that heat reaches you through moving warm air. That is convection. Now touch a metal spoon that has been sitting in something hot. The heat travels through the material itself. That is conduction. Both need matter. Conduction needs particles passing energy through a material. Convection needs a moving fluid, such as air or water. Neither can carry the sun's energy across the vacuum of space. So nature uses a third method, radiation. Despite the name, this is not automatically dangerous nuclear radiation. Radiation here means energy traveling as electromagnetic waves. Visible light is electromagnetic radiation, so are infrared, ultraviolet, and radio waves. Unlike conduction or convection, electromagnetic waves do not need air, water, metal, or any other material to travel. They can cross a vacuum. That is how the sun reaches us. It releases an enormous amount of electromagnetic energy in every direction. A tiny fraction of that energy hits Earth. It crosses roughly 93 million miles of empty space and reaches our atmosphere in about 8 minutes. The sun does not heat space on the way here. The energy travels through space and it heats matter when matter absorbs it. Picture sunlight coming through a window. The light crosses the air and hits a dark couch. The couch absorbs some of that energy and gets warmer. A light-colored surface reflects more of it. A dark surface usually absorbs more. Earth works the same way. Sunlight hits the ground, the oceans, buildings, plants, roads, ice, and clouds, and each of those absorbs and reflects a different amount. When matter absorbs the sun's radiation, the energy increases molecular motion. We experience that increased motion as temperature. This raises another strange question. If sunlight has been traveling through space for millions of miles, why is space itself so cold? Because temperature is a property of matter, and there is very little matter in most of space. You cannot heat empty nothingness the way you heat a room full of air. Individual particles in space can carry enormous energy, but there are so few of them that space does not behave like a warm atmosphere around you. That gives astronauts an unusual temperature problem. In space, you cannot say it's freezing outside the way you would on Earth. There is almost no air to conduct heat away from you. An object in direct sunlight can get extremely hot, and the same object in shadow can get very cold. The problem is not only temperature, it is radiation balance. How much energy are you absorbing, and how much are you radiating away? Earth keeps its temperature the same way. It receives energy from the sun. Clouds, ice, oceans, and other bright surfaces reflect some of that sunlight back into space. The rest is absorbed. Then Earth emits energy back toward space, mostly as infrared radiation. The planet's temperature depends on the balance between incoming and outgoing energy. If Earth absorbs more than it loses, it warms. If it loses more than it receives, it cools. Earth's climate is a giant energy budget. There is one more piece. The atmosphere does not bring the sun's heat to Earth, but once solar energy arrives, the atmosphere helps decide what happens next. Sunlight passes through the atmosphere and warms the surface. The warm surface emits infrared radiation. Certain gases in the atmosphere absorb some of that infrared energy and re-emit it, which slows the rate at which heat escapes to space. That is the greenhouse effect, and without the natural version of it, Earth would be much colder. So the sun sends energy through radiation, the ground absorbs it, and the atmosphere helps redistribute and hold on to some of it. That is why sunlight can heat Earth, even though space contains almost no air. You can test this yourself. Go outside on a sunny winter day. Stand in direct sunlight, then step into the shade. The air temperature may be almost the same in both spots, but you feel the difference right away. In direct sunlight, your body absorbs extra electromagnetic radiation from the sun. In the shade, that direct solar energy is blocked. The air did not get colder. You stopped receiving as much radiation. Before we continue, if you enjoy simple science questions like this, the kind that seem obvious until you think about them, take a second to like the video and subscribe to Dreamframe TV. It helps the channel grow, and we have a lot more strange science questions coming. If radiation can cross empty space, can heat from Earth travel back into space the same way? Yes, it has to. Earth continuously radiates energy outward. Everything above absolute zero emits electromagnetic radiation. You, your house, the ocean, the planet. Most objects at ordinary temperatures emit mainly in infrared wavelengths that our eyes cannot see. So right now, your body is radiating energy into its surroundings. You cannot see it, but thermal cameras can. That is why people glow in infrared images. The sun is much hotter, so it emits huge amounts of radiation across many wavelengths, including visible light. Earth is much cooler, so most of the energy it sends back toward space is infrared. This is Earth's energy cycle. Energy arrives mostly as sunlight. Earth absorbs part of it and warms. Then Earth releases energy back toward space as infrared radiation. So why doesn't the sun keep heating Earth forever? Because Earth is also losing energy the whole time. Under relatively stable conditions, incoming and outgoing energy approach a balance. If Earth had no way to release energy, temperatures would keep rising. But radiation works both ways. The sun radiates toward Earth, and Earth radiates toward space. Now imagine removing the sun. Earth would lose that enormous incoming supply, but it would keep radiating heat away, so temperatures would start falling. The oceans and atmosphere store heat for a while, so Earth would not freeze instantly. Over time, though, the loss would become enormous. This is why the sun is much more than a bright object in the sky. It is the main energy source driving Earth's climate. It warms the surface, powers the water cycle, drives winds, and supports photosynthesis. Almost every food chain eventually depends on that incoming energy. All of it crosses a vacuum to reach us. No air, no physical connection, just electromagnetic radiation moving at the speed of light. This also clears up a common misunderstanding. An object closer to the sun generally receives more solar energy. That is not because the space near the sun is like hot air near a fire. It is because more radiation strikes each square meter of the object. Move farther away, and the same energy spreads across a larger area. That is one reason planets at different distances have such different energy environments. Mercury receives far more solar energy than Earth. Mars receives less. Planets far beyond Mars receive dramatically less. Distance from a star matters enormously, but the empty space in between does not stop the energy from traveling. So if space is empty, how does the sun heat Earth? The sun sends electromagnetic radiation across the vacuum. That radiation reaches Earth. Matter absorbs it. The energy becomes molecular motion, and the planet warms. Next time sunlight hits your face, think about what just happened. That energy left the sun about 8 minutes earlier, crossed about 93 million miles of nearly empty space, and ended its journey on you. Space may be empty, but empty does not mean energy cannot cross it.